The fundamental theorem of arithmetic. Well, we will not state the theorem first. Rather, we will play with some numbers, and I think by the end of that, when we have worked out some examples or some numbers, you will see that you could have come up with the theorem by yourself. So we will factorize numbers and then we will multiply numbers to see, is there something special about numbers, or is there some pattern when we factorize or multiply numbers. So I'll begin with 4, which I can factorize as 2 times 2, then 12, which can be factorized as 2 times 2 times 3, that means 2 to the 2 times 3, then 49, 253, 1771, 5313, which can be factorized as 3 times 7 times 11 times 23, then 10, 626, which is 2 times 3 times 7 times 11 times 23, and so on. Now you can see this number, which is 7 times 11 times 23, 1771 that was, and this number, which is 12, and other numbers. Well, there is something very special or let's say peculiar about this number, which is that these numbers, say 1771, 12, 5313, and so on, all these numbers are composite numbers. That means these numbers have more than one factors other than 1 and the number itself. And then the factorization of these numbers, or the factors of these numbers, the way we have expressed them. And you can see that these numbers, when I have factorized them, then all these numbers are a product of primes. For example, 1771, it is 7 times 11 times 23. And you can look at any number and see that it is a product of primes. Or a product of powers of prime. For example, this number 21252 is 2 to the 2 times 3 times 7 times 11 times 23. Well, in essence, all these numbers are a product of primes. Now I can try multiplying numbers, or in other words, I decide the factors first, then the number. So 7 times 11 times 23, 1771, then I add one more number to it, and this is 29, which is 51359, and then I multiply. Well, I take one number out and multiply by some other number, which is 4, that's 308, and you will see here the number 4 is, I can further factorize it as 2 times 2. So I can write it as 2 times 2 times 7 times 11. And let's try one more number, multiply it by one more number, which is 10. So this is going to be 3080. Well, I should have taken an odd number, but let's stick with it. It's 10 here. So this number I can further factorize at 2 times 5. Well, now the question is that I can produce every composite number by multiplying this way. I mean, I can multiply even in odd numbers, but eventually I can always express them as the product of primes. So can I produce every composite number this way by multiplying only prime numbers? And if not, is there a composite number that is not a product of primes? Well, you have to think about it. Can I get a number by multiplying numbers, and these numbers are not primes? Well, so far from the numbers that we have worked out, we know that we can always express every number as long as it is composite as the product of primes. So by that observation, it is not possible, but you can try. And then we get to the theorem, which is that every composite number can be expressed as a product of only primes. That's what we have seen, that even if you try to multiply numbers which are not primes, for example 4 times 7 times 11, but eventually if you break down the number 4 or factorize the number 4, then that number is going to be a product of primes too. So the whole number again will become a product of primes. So that's what the fundamental theorem of arithmetic says, that every composite number can be expressed as a product of only primes. But is there something unique about expressing these numbers as the product of primes too? Let's see this number. So you can express it as 11 times 7 times 23 times 29, or you can say it is 7 times 11 times 23 times 29. Well, the number is in ascending order. Then you can say 7 times 23 times 11 times 29, a random order, or you can say 29 times 23 times 11 times 7. The factors are in descending order. Now if you look at the factors when I have arranged them in ascending or descending order, and if you put them, and if you put these factors in order, in certain order, ascending or descending, then you really have no other way to expressing these primes, right? You can, if you take a random order, then you can have as many combinations of these as the factors we have. But once you arrange them in an order, then you have only one way to express them. That means when put in a particular order, the factorization is going to be unique. That's what the fundamental theorem of arithmetic is. And because it is a theorem and it is always true about numbers, then you are going to use this theorem to solve a lot of problems. And these problems are going to be divisibility. We are going to determine divisibility of a number, then determine last digit of a number, and the most important is you are going to prove that a number is irrational using the fundamental theorem of arithmetic in this chapter. And we are going to solve a lot of examples to see how we can apply this theorem.